All right, so usually I write quickly on the blackboard what we have seen last week, just to refresh our memory. Of course, it's a summary. So we define on a set what is a binary relation. It's just a comparison of two objects in this set. And we have defined what means if the binary relation is reflexive, symmetric, asymmetric, antisymmetric, complete, and transitive. These are quite simple definitions. And I will call a decision problem a set with a relation, and usually we are going to write it like this, which is complete and transitive. So this is a set with a binary relation, so you can compare the elements of the set. Complete means precisely that you can compare all of them, and transitive has a specific meaning. And whenever you have such a set with, if you have these two conditions, it's called a weak preference. So whenever you have a set on a weak preference, you can also define what is a strict preference, which would correspond to a strict inequality. I should write the sign. And what is indifference, which is an equivalence relation. Now, we would like to represent this system with numbers. So I define what is a utility or a payoff. This is the second word. It's a function from A to the set of real numbers, which represent this weak preference in the following sense. U of A is bigger or equal to U of B, and this is just a comparison between two numbers, if and only if A is preferred on B. So you can represent this relation or the relation between A and B by a relation between numbers. And you can wonder if this always exists. And I gave two statements. If A is countable, countable means you can enumerate the set like n, then it always exists. Or if you have a subset inside A, and this subset is countable and order dense, you can approximate any two elements in this by another element in between, then there also exists a utility function. So this is very convenient because now you deal with numbers. Then if I add some more structure on A, so if I assume that A is inside a vector space, the typical vector space is Rn. But the point is, in a vector space, you can add two elements and you can multiply an element by a scalar. And then I define what means a convex set, which is precisely meaningful if you're in a vector space. We say that a utility is linear if it satisfies this relation, which is very convenient. U of a linear combination, T is between 0 and 1. So U of a linear combination is equal to this linear combination of U of A and U of B. So it's called a linear utility. And again, you can wonder, does it always exist when you are in this setting? The answer is if and only if this relation is what is called independent and continuous. And I gave the definition of independent and continuous. And if you just look at it, it's maybe a bit complicated, but if you think about numbers, these two conditions are quite natural. And for information, these four conditions, so a relation which is transitive and complete, this is essential because it's the first conditions we put. But in addition, if this relation is independent and continuous, we say that it leads to a rational behavior. And these four conditions are even called the four axioms of a rational agent. This is what we will require later. And at the end, I just introduced one more thing, and I will finish with this very quickly. If you take a set, you can, so this is the set A, you can look at functions defined on A taking positive values, such that the function is only defined on a few points. For example, this function is only defined on 3 points of A, and the sum of these three values has to be 1. So for example, 1 over 3, 3 times. This is, if you look in a slightly more general framework, it's called a simple probability function on A. And so let me finish. It will come back. We will come back to this setting next week, but it's good to already introduce it. What about taking a linear combination of two such functions? If you take, let me call these two functions P and Q, I take two such functions, then you can easily check that Tp plus 1 minus Tq is also an element of this set. So it's a linear, it is inside a vector space, and you can manage so that it is convex, and you can check that it's convex. Okay. And I call it a simple probability function, but I need to say the name that people use in game theory. So if A is a set of, these are just names, alternatives or strategies, we will see this a little bit later today, then P is, so such a function is called, I don't like this name, but it appears, it's called a lottery. Let's say P, or this PS of A is called the set of lotteries. This is how people in game theory or in economics call this. But these are just functions with finite support and summing up to 1. But they call it lotteries. And the last thing I want to mention about this, you can wonder, okay, it's a convex set. Do we have a preference, which is a weak preference, and even which is independent and continuous? So the answer is yes. So we are quite happy. Let A be an arbitrary set. Then they exist. Now I'm allow myself to use this. It means they exist, or it exists, or they exist. They exist. They exist a weak preference will denote it like this on the set PS of A. So on the, it's not so simple because we are dealing with a set of functions. So there exists a way to say which function is better than the other one. So there exists a weak preference on this set of function, which is independent and continuous. So the two conditions I mentioned before for rational behavior, if and only if, and only if, exist. And it's quite simple. There exists a U from A to R with P. Can you still see the last line, or is it visible? Okay, if not, you just tell me. If this sum on A, I let you think for a second about this. What does it mean? Again, we will play with this next week, but I have this set of functions, and you can think about it. We have different strategies, and we are going to do a kind of combination of these strategies. And this represent the percentage of each strategy that we will consider later. So we can find so this is, let's say, a P. This yellow one is the function P. And I have a different one with, let's say, 1/7 and 6/7. It still end up with 1. So we have two such functions. These are P and Q. And I want to say which one is the best one with a certain relation, which is a weak preference, which is independent and continuous. You can check the meaning. And we can do it if and only if, and it's a very weak requirement, there exists a function on this space with value in R such that this preference is in fact given by this condition. And what is this? And please look, observe, it's a sum. I should write A in A on A in A, which is a bit annoying because if A is very big set, it would be a very big sum. But look, there are only a few points where this is not 0. This is why I have this assumption the support is finite. It means this sum is in fact a finite sum. You take only a few number of points and you do this sum, the value at A of P times the P of U of A. And you do this finite sum, let's say for the yellow function, and this is a number, and you compare it with a number given by the sum Q of A times U of A. Or maybe I can use a different, because these points might be different. So I put a yellow simply because these numbers, P of A is most of the time 0, except on a few points. And here, Q of A is also 0 most of the time, except on a few points. But these points can be different. So it means we have a way to order these functions by a comparison between numbers. And it's an if and only if. And whenever you do this, it means this relation. So be careful, this is this curly relation on this set PS of A, whenever you can compare the numbers on the right. Okay? And this is called, this has a nice name. I like this name. This function U is called, in this context, von Neumann Morgenstern utility function. Of course, these are the name of two persons. Okay. So we will come back to this, but it's good to have a first understanding of this concept of functions on A, and we can order this function on A if we can find a U, just a function from U from A to R, and construct this. Any question or remark? Yes.
This is the discrete problem.
Yes, I can. You also asked this question. I said P and Q are with a finite support. You can extend this on a more general framework. If you have A, you can define functions, but then you need a measure on the set A. So you need more structure. You need a measure theory on this set A. So that's why I prefer sums. But yeah. Then it will be an integration, yes. But I want to keep things simple. And even in some books, they take this set finite. And I don't want to take it finite, but at some places they take it finite because in the application, it's often sufficient. But yeah, everything can be extended. Okay, chapter 2 is about strategic game. I need to introduce what are strategic games. And in fact, they're very simple. So these strategic games are simple model. Why? Because all players, by the way, a player is not always somebody really playing. It's also sometimes just one person, and I will call agent. So one agent or one player make their decision. The point is that they make their decision simultaneously and independently. You can already figure out that this is not the most general situation because players play at the same time and independently. But this is the first model. So they play simultaneously and independently. We assume each player is rational. And what do I mean by this? And now I have to make a simplification. I will call the player he. If you want to use she everywhere, if you want to use anything else, you can. I simplify my life. It's already complicated enough to prepare this note, so please allow me to use. I know it's not politically correct. No, for some people, no, for some people, it's not fair to use only he. I'm not sure. Okay, so please, if you want to change, you can use other name. I will use he or his. So he's a player. He's rational in the sense he wants to get the highest payoff or the highest value of the utility function. This is the same. But in this context, we say the biggest value of the payoff. But just for its equivalent to highest value of utility. Wait, let me finish the sentence of utility function. Yes, what is the question?
Axioms were equivalent to rational behavior.
Yes. Yes. So it means precisely whenever we play these games, the four axioms will be underlying or below this. Okay. And that's it. Okay, so we will play games with these assumptions. So now I need to define what is a strategy game. Or what are strategic games? Okay. We assume that we have n players, and I will denote them by the first one, the second one, up to the nth one. This is a set of players. So I give just the name 1, 2, 3, up to n to these n players. I don't give them a precise name. And AI is going to be the set of strategies of player I. So the same set as before, but now we have n players, so we have n sets, the set of strategies of player I, and UI is going to be the payoff function or utility function for player I. Oh, what I introduced before without the I is now with the I, so we have n sets AI and n utility function or payoff functions I with the index I. Okay. So that's quite natural. And now what is a game? In this subject, I observe you have to be very precise with definition, because otherwise you simply don't know what you're talking about. So we have to be really to stick to the definition. Be careful with this. Definition. N player strategy game. It's rather simple. N player strategy game. I'm going to denote it by G, but it corresponds to two objects. So I call it G, but it's A and U. And what are A and U? A is just the set of all points A1, A2, up to AN, so that A1, AI, or AI is in. So it's like an n vector. You can think about an n vector. This is like an n vector, so it has n components. And each component is in the set AI. The first component is in the set corresponding to A1. The second entry is in the set A2, and so on. Okay. And this set A is called the set of strategy profiles, because it contains all strategies. Please be aware, it contains all strategy for the first player, it contains all strategies for the second player, and so on. And what is U? What is U? U is it's also a vector, but it's a vector made of U1, U2, up to UN. But there is one subtlety. Maybe you have observed that I didn't say this UI. I didn't say from where to where. I didn't. So you can. U1 is going to be defined on all strategies. U2, and it will be clear in the examples. U2 is going to be defined on all A. U3 also on all A. So it means this is going to be defined on n copies of A. Each function is defined on one copy of A. So you have AN. And the value, each function is with value in R. So we have n copies of R. So it takes value in Rn.
It's like one player as a specific,
We will see in a second in the examples. So if you don't understand this completely, just wait for the examples. But it's clear I need to take into account all possible strategy of all players. And these payoff functions, each of them is defined on a copy of A. So if I have n functions, I need n copies of A and its value in Rn, because each of them has value in R. And this U is called the set of payoff function. It's a collection of all these payoff function for each player. And remember, in this game, players play simultaneously and independently. So one player doesn't know what another player is going to play. So I have 4 examples in the notes. However, it takes quite a long time to present all of them, so I don't know yet. But please, if I don't present all of them, please look at the notes. The first one is the most traditional one. It's called the prisoner dilemma. Okay. So everything is written in the note, so I can sketch here. So we have two suspects or two prisoners. And they are guilty or they are suspected of two things, of robbery, so something quite small, and a crime, which is more important. Okay? So these two guys are suspected of both a robbery and a crime, and we know that they are guilty. We know that they've done this. We have no evidence that they committed this crime. So this is a setting. Two guys in a prison separately. They are separated. They are not together. Okay. And they have two options. So the set AI is they have two strategies. Either they can confess or not confess. So C is for confess, and NC is for not confess. The crime. Because the robbery, we know that they are guilty, but they can either confess or not confess the crime. And now we have two utility functions. And, oh, no, I need to define one more thing. So this is AI. Both can confess or not confess. So it means the set A, if you look at my definition, it contains four options. Either both confess or only the first one confess. Oh, no, I take it. Okay, I take it in the same order. They cannot confess, not confess. This is the first option. If the first one cannot confess, the second one can confess, or confess, not confess, or the two confess. And you can check it's indeed all possibilities that we have defined here. So this represents the first prisoner, this is the second. And now we have U1, we define U1, I will explain, U1 of, I take the second one, U1 of C and C, U1. So what does it mean? U1 is, as we know, the utility function or the payoff of the first prisoner. It depends, it's a function on this. So we have four possible points. So U1 of both not confess, U1 of the first one not confess, the second one confess, and so on. And I assign some numbers which have a meaning. We will see in a second. Of course, it's just an example. And these numbers are years in prison. So what does it mean? If none of them confess, we have no evidence that they have made a crime, so they are just guilty of robbery. So that's why they get both 1 year. If they both confess, it means they both say they committed the crime. Each of them is going to receive 10 years. So this is also U2 of CC, and this is also U2 of NC. But we have two utility functions. And now what about this? If the first one does not confess, and the second one confess, then they will use the second one for making the first one guilty. That's why here, the first one is going to receive 15 years in prison. And in this case, okay, no, I continue with the first one. On the other hand, if the first one confesses and the second one doesn't, they will use what the first one say in order to give a sentence to the second one, and the first one will be free. Okay, it's a rule. And now we have also U2. This 15 years is U2 of confess, not confess. And this is U2 of not confess, confess. It's explained again in the note. Okay. So now you can see we define this set A, and the payoff function have to be defined on A. So we have 4 points for the first one. We have 4 points on the second one. Okay. And there is a way to encode this just in a small table. It contains the same information, but it's just one table. And it's again in the notes. It's a table. So we have not, the first line is for the first prisoner. And the first column, not confess. Confess is for the second prisoner. And now I want to have in each entry the vector with the two entries U1 and U2. So if both do not confess, we have -1, -1. This is a vector. -1, -1 is in fact U1 of NC, NC, and second entry U2 of NC, NC. This is the vector with the two entries. And you can fill this table. You have 0, -15, -15, 0, and -10, -10. Okay. So it contains the same information. Okay. What is the trick with this example? First, I wanted to do it because it's the first example, but also because you see what is AI, what is the set A, and what are these functions on 4 points. Now you can wonder, these two prisoners are separated. Which strategy they should use? They cannot communicate. And it turns out that each prisoner the prisoner, remember, supposed rational, should confess both. And we will see why. Because the first prisoner, if the first prisoner confess, he doesn't know what the other one is going to do. So if the first prisoner confess and the second one, so why the first prisoner should confess? Look at the first line. If the first prisoner confess and the second one, okay, no, now I'm lost. You have to read it carefully. Okay. Wait. No, you really have to, really have to read it horizontally. But why they should confess? Because the best payoff is confess. Yes, look at these two entries here. First, you compare these two entries. If the second prisoner does not confess, for the first prisoner, it's better to get 0. We want the highest payoff. So we should choose 0 here. And independently, if the second prisoner confess, again, we have 10 here. So if the first prisoner is rational, always 0 is better than -1, -10 is better than -15. So the first prisoner should confess. And the same reason for the second one. So if a prisoner is rational and cannot discuss with the other, he will confess. And so it means this, at the end of the day, this is what will happen if both prisoners are rational. This is called the prisoner dilemma or paradox. But I wanted to say it because we see the different object, and it's a non-cooperative game precisely because the two prisoners cannot communicate. If they can communicate, probably they would choose another option. But for now, they cannot communicate. It's a non-cooperative game. So this is the first example. Let me state a second example. Which is, okay, it has a certain name. Now we have n agents. They produce the same thing, so it's called the same utility. They all produce umbrella, the same utility, the same commodity, sorry, the same commodity. And agent I produce a certain number AI of these commodities, which is this AI is any positive number between 0 and infinity. We assume that it can be a fraction, whatever. So agent I produce AI commodities at a price. Of course, they have to pay a certain price for producing this at a price which I denote by Ci of AI. So it means the price depends on I. So of course, if the agent produces a small number of commodities, the total price will be less than if it produces a lot of commodities. Now, there is one more thing. The price for selling these commodities depend on how many are available, which is quite clear. If something is if you have a lot of them, the price is different than if you have very few of them. So the price for selling these commodities, I'm going to denote it by, it's a function of the sum of all commodities. So the price depends on this total number of commodities. This is a certain model. Okay, so now we understand this model. Let's put it in a better framework. So AI, the agent can produce any number of commodities. So it's R plus, and R plus is just 0 infinity. So it means A is n copies of this, one for each agent. And U is U1, U2, UN. And now you can wonder, what is A? And for what is UI? And again, you observe that UI is going to depend on the number of commodities produced by the first one, the second one, up to the nth one. Why? Because the price depends on the sum. So it's really a function depending on the production of each agent. And if you look at what I have written, we can define this because the agent, so what is the payoff of agent I? It's the price for one commodity. This is the price for one commodity. So the money that the agent is going to get is this price per commodity times the number of commodity. Oh, I should use a different letter. Otherwise, somebody will complain. I use a different letter because, look, I do this sum. This gives me the price per commodity. And the agent I has produced AI number of such commodities. So the money he can do is this, right? But now he has also to use some money for producing these commodities. So the money or the payoff is this. So again, it's good to look at this example because we have this set of strategies, and the set of profile of strategies contains all possible productions of this commodity. And now the payoff for each agent depend on how many commodities are produced by each agent, because the price depends on this sum, times the number of commodities produced by agent I, and the price this agent had to pay for producing these commodities. Okay. So it's good to have these two examples in mind. Okay, I can quickly go through the third one. Do you have any question? And if online you have a question, you can also ask me. You can just interrupt and ask your question. Before the third example, let me just introduce a notation which is very convenient. If you have a vector, if you take n numbers, maybe I shouldn't use A. Let's take x1, x2 up to xn, an element of Rn. I want a vector, so it means this is just a real number. This is again a real number, and so on. If you take a vector, I define a certain norm. I call it x, this vector. I'm going to call it capital X. It's just a vector. I will define a certain, it's called a norm with this index. So I need to give you a definition. I take the maximum on I of x. So what does it mean? You have n numbers. They can be positive or negative. So you take the absolute value and you take the maximal one. Okay, this is just a definition. I define this a norm infinity as just the maximal one. And in calculus 2, you should look at this. But I'm not teaching calculus 2 anymore. Okay. But this is nothing complicated. If you have a vector 1, 5, minus 4, you can tell me what is its infinity norm. You take the absolute value of these three entries and then the maximal one. So it's going to be 5. Okay. I need this notation for the next example. It's about an auction, a very simple auction. It's a first price. Example 3, first price auction. So we have again n agents want to buy something. And they want to buy X. Okay. And they assume this is whatever you want. Okay. And each agent agent I should write. Agent I evaluate X at the price, which I'm going to call VI. So you're saying that X is only $10, while somebody else can think that this is worth $20. But you don't say this number to anybody. This value is known only by I. Of course, you're not going to tell to everybody how much you think that, what is the value of this X. And now what is the game? Everybody is going to give a number. And the one with the highest number is going to win, but he has to pay the price. That the highest price. So each agent is going to propose a price. And it means this price is going to be AI. And the one proposing the largest value, wins and pay. What is the price it's going to pay? It's going to be precisely the maximum. That's why I introduced this notation. So each agent has a certain price in mind. Now each agent is going to say, oh, I'm offering this price. And the one which proposes the highest price is going to win. But of course, if you think that something has a value of $10, and you say, I'm going to pay 20, it means you are ready to pay more than the value you expect for this object. So it's a tricky situation. But if you propose a price which is too low, you are not going to win. So what is the framework for, there is one more rule. If two persons propose the same largest value, this is possible if two persons propose $1 million. If this is, if two agents propose the same highest price, we choose, this is just a choice. We choose the one with the lowest index. Of course, this is a very simple rule. So if you have agent 3 and agent 4, which propose the same price, the highest one, we are going to choose 3, number 3, yes.
But if you knew your index, then will that somehow change your strategy?
Yeah, we don't know how it's indexed at the very beginning.
Oh, okay.
It's random. It's randomly indexed at the beginning. So you can wonder, what is the setting? First, what is AI? Again, AI is between 0 and infinity because anybody can propose a price between 0 and infinity. Then it means that A is again n copies of this. And I'm going to take A1, A2, up to AN. So this is going to be the price offered by the first one, the price offered by the second one, and the price offered by the nth one. And what is UI? UI of A, it's a bit subtle, so you need to think about this. It's going to be VI minus AI for I, which is given by, this is a minimum probably you cannot see, for I, which is going to be the minimum over J of J is a. Okay, it's so what you need to think for a second. As I said, we are going to take the one with the highest price. So we take the AJ. It's my example is no more here. It was a 5. We are going to take the agent which propose the highest price. But if there are two agents, then we take the minimal index. So this is a way we choose a minimum index if we have more than one agent which propose a maximal price. So we take the minimum over J of those guys, those agents who propose the maximal price. This is exactly what I've. So this is the utility value for the winner. And for the other one, it's 0. Otherwise. And here you can see something. This number can be either positive or negative. And it makes a difference because if you estimate, if you think that it's worth a certain value, VI, you can either propose a higher or lower one. And if you propose a higher value, maybe you have a better chance to win, but in fact your payoff is decreasing because you, compared to what the price you think about this object, you are losing money because you pay too much. On the other hand, if you win, but the price you propose is lower than what you think about this object, then you have a positive payoff. There is one more example in the notes, which is quite similar. But I wanted to spend a few minutes on these 3 examples because we have defined what is a set of strategies for all agents, then what is a set of profiles of strategies, and then we have seen 3 utility functions. And always be careful, you need the information about everybody. You cannot define UI only with the information from AI. UI takes into account the price or the payoff by all agents. Okay. We move to the next section. Now we know what is a strategic game. We have a way to formalize these games with the set A and the set of utility functions U. What is 2.2? What is a Nash equilibrium? Yes.
There's no clear option if you draw it in a table to decide.
I do not tell you now what, it's indeed a good remark. I'm not claiming or I'm not saying what is the best strategy. And it's not clear yet. I'm just, we are just at the beginning. I'm describing the framework. And indeed, choosing the best strategy, if I could give you the best strategy, I would probably be rich. And I wouldn't teach anymore. Yes?
Agent, wouldn't you always say that AI is going to be less than or equal to UI?
Yeah, but if it is a rational agent, probably yes. Yes, you're right. Because otherwise, indeed, you would get something negative. But just based on this, I didn't say that the agents right now are rational. But yeah, they will be assumed to be rational. But yeah, you're right. You wouldn't propose a price which is bigger than what you have in mind, because then it would be, you would decrease your utility function. Okay. So what is Nash equilibrium? It has been introduced by Nash, of course. I will give a precise definition, but it is a strategy profile. So it means it's an element of A. A strategy profile is a collection A1, A2 up to AN. And I put a star because it's precisely a special one. So it's a strategy profile so that I will give a more precise definition in a second, so that no player gains, increase its utility function when, and this is important, unilaterally moving from it. This is just a sentence. I will make it more precise, but it means it's a special point. It's a special point in the set A, so that no player will get or will increase its utility function when moving outside of this point. And unilaterally means just one player. And we will see in a second. So now let me be more precise. Definition of a Nash equilibrium. So these are, we have this big set. You should think like this. We have a big set of all strategies. It's difficult for each player to say which one is the best strategy. So I first define some special points inside this set of strategies. And Nash equilibrium points are some definitions. So now that's more precise. For a strategic game, remember it's written AU. For a strategic game AU, a Nash equilibrium is a strategy profile. A strategy profile. So it's a point A star. I put star inside A. It's a specific point. And this it has n coordinates. So it has A1 star, A2 star, up to AN star. And as I said, it's an element of A, satisfying. So UI at A star has to be bigger than now. So look at what I have written. I have written UI at this specific point is bigger than UI at A1 star, A2 star, up to AI n-1 star. Then here there is no star. So I choose an arbitrary point AI. So this is true for any AI inside AI. So it's a point which is bigger. So it should remind you a maximal point that you see in calculus, but be careful. It's less general than a maximal point because I look at one function, but I'm saying that just that it's maximal for one variable. There is a small thing. So this has to be true, satisfying for all I from 1 up to n, all I belonging to the set 1 up to n, this condition. And if you think about it, it means exactly this. The utility function cannot increase by moving away from this point. So please think about it a second. If this point is special because it's big, the value is bigger than any other point when you change only one variable, the variable I. So it's like a maximum. Yes.
So it's almost a goal vessel, but if you change two at the same time, then it can.
You change only one.
If you change only one, then it can.
So I cannot represent in many dimensions, but indeed it means in one direction it's a maximum, but you don't know anything in the other direction. That's the point. So it's a, but you have, these are different functions. So for the function I, it has a maximum in this direction I. Now if you take a different function, so if you take a different j, then it's now in the direction j that you have a maximum. So be careful, this I here, the function you consider is the same index as this one. And it's only for each function I, it's a maximum only in one direction. So that's why it's related to local maximum, but it's still different. Now, exercise. Oh yeah, your question.
Yeah, it's my question. Is it the strategy would be available to every player, would it? And it has to be the same Nash equilibrium.
Yeah, Nash equilibrium, look at the definition. It's a point such that this is satisfied for all I. That's it. Now, good question, does it exist? Nobody said that it always exists. But now there is an exercise, and probably you can find many of this type. So and I encourage you to look at this for the 3 or 4 examples that you can find in the note. For the examples in the notes, a Nash equilibrium exists, a Nash. So you can check, but be careful, I'm not claiming that it does not always exist. In general, it does not always exist. And if it exists, it might not be unique. Not be unique. Nobody said that you have only one. In my picture, I represented 3 of them.
Or any AI. So isn't it the same for every player? Then it's unique.
I'm not claiming that this point is unique. And in the note, if you solve for the 3rd example, or for the 4th one, which I did not present, you will see that it's not unique. No. Or maybe even for the 3rd one. For the prisoner dilemma, it's unique. For example 2, I encourage 2nd-year students to look at it because you have to do, you can solve this with some partial derivatives. When you have some functions in a setting where you have partial derivative, this can be solved with partial derivatives. But first-year student might not know what is a partial derivative. That's why I do not present it here, but it's an exercise, and I encourage you to think about it. And there is another example in the notes. I do not reproduce it here, but there is an example which is called the matching penny games, where you don't have a Nash equilibrium. So this is a very simple example where you don't have, it's in the notes, you don't have a Nash equilibrium. Okay. So I gave a definition of this. We will see that they play an important role because they allow us first to have specific points in the set of strategies. And now, why Nash became famous and got the Nobel Prize It's not because of this definition, but because also he proved that for some system, a Nash equilibrium exists. So Nash theorem, and I'm going to state it, the proof is not at all trivial. Not Nash theorem. Just before I state it, it proposes sufficient conditions for the existence of a Nash equilibrium. But be careful with what I have written. When I write sufficient, it means if you list the conditions I'm going to write, you have a Nash equilibrium, but it doesn't mean if you don't have this condition, you don't have a Nash equilibrium. They are sufficient, but it doesn't mean that they are necessary. So you may have a Nash equilibrium even if the conditions I'm going to state are not satisfied. So the word sufficient is important. It means if you are in this framework, yes, you have, but it doesn't mean if you are not in this framework that it doesn't exist. And we will see, for example, that it does not apply to the examples I proposed before. So I was a bit disappointed by this. But nevertheless, let me state it because it's an important result. So we consider G, which is this set AU, a strategy game. With n players. With n players. And assume that for each agent I, I'm going to assume three conditions. The set AI, which is a set of strategies of agent I, AI is not empty. Of course, I don't want to have the empty set, which means no strategy for the agent I. So it's not empty, but it's a convex. We know what is convex, bounded, and closed subset of R, N, or Mi. So what does it mean? And we can already see that it's not satisfied by any of the models I introduced. We have Rn, and this dimension can depend on I. So let me take R2. The set of strategies this is one assumption, is essentially like this. This is the assumption. It's not empty. This is let's say A1. It's not empty, it's convex. Remember, convex means whenever you take 2 points, all points in between are inside. It's bounded. Bounded means you can put it in a box. And closed means that the boundary belongs to the set. So the boundary belongs to AI. This is a notion of here. And for example, for the prisoner dilemma, it's clearly not possible because we have only 2 points. For the other example, remember AI was a half line, 0, infinity, which are not bounded. You cannot put this in a box, and still it is convex, but it's not bounded. So you can already see that it does not apply to.
Convex needs 0 to be
It is convex. Please check. Okay, but still, this is a set of one condition that Nash proposed. The utility function is continuous on A. A is a collection of A1 and A2 and A3 up to AN. I introduce it. So it's a continuous function on this set. And there is a third condition. There's a third condition, which is not completely trivial. For any fixed Aj belonging to Aj for J different from I, we will see. So I take all variable fixed except one. The function what is the function I consider? AI, take a point AI, goes to UI of A1 to AI minus 1, AI plus 1. This is just a real number. So maybe you haven't seen this notation before. What I want to write with this notation, I'm considering a function of only one variable. The function AI goes to this with the AI here. So it's a function of one variable. All the other one are fixed. You fix a point A1, you fix a point A2, and you consider just the function of one variable. Okay? It's a function of one variable, and this variable is in the set AI, the definition. So for all fixed Aj, except the variable I, this function is what is called quasi-concave. I gave the definition in the notes. It's slightly more general. It's slightly more general than concave. But concave is easy to visualize. A function is concave, essentially, if it looks like this. If we want to be precise, and because I have to state it precisely, I need to say the slightly more general condition. That's why I put quasi-concave. You can look at what it means. But if you have concave in mind, this is sufficient. You know, you don't need to have the most general. I need to write it, but you don't need to keep in mind this quasi-concave condition. But it said that essentially you have a function of this type for each variable. So for the function ui, it has this form. And you shouldn't be surprised by this condition, because if you remember the Nash equilibrium point, I already showed this. And in the variable, if this is ui, in one variable, it has to have a maximum. So you are quite naturally with this notion of concave. You don't have to understand all the details, but this is Nash's theorem. It gives us certain conditions in a certain framework. Oh, I didn't finish the statement. So if we have these three conditions, then you can finish by yourself. Then a Nash equilibrium point exists. Then a Nash equilibrium exists. So we define what is a Nash equilibrium, and there is this rather deep result which tells you in a certain framework with these three conditions satisfied, there exists a Nash equilibrium. But it doesn't tell you that if you are not in this framework, that a Nash equilibrium does not exist. You don't know. And indeed, for the 4 examples I gave before it exists, even though this condition, essentially this one, is not satisfied. So keep it in mind, this is a sufficient statement. Okay, Nash equilibrium point or Nash equilibrium are important, and we will probably come back later. Do you have any question either online or here? I don't know if there is anybody online, but I can see 4 persons, but I can see only 4 black squares. No. Okay, so let's move on now. The next, among the set of strategic games, some are easier than other ones. And always we start with the simplest one. The first one, or the first subfamily, is called, this is 2.3. This is 2 players, zero-sum games, or strategic games. So 2 players we understand. I will have to say what means zero-sum. The idea is the loss of one player is automatically the gain of the other. So I need to give you the precise definition. So 2 players, zero-sum game. Is a strategic game. G with 2 sets, and sometimes I'm going to write this A1 times A2, because if you look at what I have defined, the set A is exactly the product of A1 times A2. You can think the 2 dimensions, think about the 2-dimensional plane. The 2-dimensional plane is 1 copy of R times 1 copy of R, and any point has 2 coordinates, x, y. The first coordinate is here, the second coordinate is here. So this A1 times A2, it's the same. You have A1, A2, and every point has a first entry in A1, a second entry in A2. And we have 2 functions, U1 and U2. So in this, by writing this, I emphasize that it's a 2-player game. It's a strategic game G with this set A and these 2 utility functions, such that U1 of A1, A2, this is just a number, plus U2 of A1, A2 is 0. So the sum of the utility function 1 and the utility function U2 is 0 for any A1, A2 inside the set A. This is the set A. This is why it's called zero-sum. And please observe that clearly this is equivalent to U2 of A1, A2 is minus U1 of A1, A2. E1, 2. Okay. So it means you don't need the definition of both U1 and U2. If you have one of them, you know everything. If I give you U1, you can tell me what is U2, because it's just a negative. So I'm going to just keep the information on U1, because U2 is not necessary. So we shall write G is A1, A2, U1 for such game, because I don't need A2. Sorry, I don't need U2. A1 and A2 can be different, but if I have U1, automatically I have U2 because it's negative. Okay, so for a zero-sum two-player strategic game, I will just write this. Okay. And for the next definition, we assume, which is a natural, we assume U1 from A to R is bounded. What is a bounded function? You probably know what it is. Let me draw just a picture on one line. If I take the real line R, if I draw a function like this, it's going to be bounded, the function. If I draw a function like this, going to infinity, it's not bounded. So what is a more precise definition of bounded? A bounded function, it means there exists m bigger than 0 such that minus m is smaller or equal to u1 of a1, a2, smaller or equal to m for any point, any a1, a2. This is a bounded function. It's between a lower value and an upper value. That's quite natural. For example, the function x goes to x squared. You probably know that it's not bounded. While the function x goes to sine of x, the sine function, you probably know that it's bounded. Okay. So this is the notion of a bounded function. There is a value which is smaller than all possible values here, and there is an upper bound. Okay. So I will assume that U is bounded because I need it for the next definition, and it's quite natural. The payoff cannot go to infinity. And now you have to be a bit careful because the following two definitions are not so simple. You have to think about them for a second. So I assume that U1 is bounded, and I'm going to define the following function, two functions. It's a capital lambda. This is called lambda, but I underline it, and it's a capital letter, capital lambda. I underline it. Capital lambda, it's going to be a function from A1 to R, so only on one variable, and I need to define it. This lambda of a point A1 is infimum over all A2 belonging to U1. Try to think about this. What does it mean? And I directly write a second one because it's the same type, A2 to R. And now lambda, which I cover by A2, it's going to be a sup on A1 in A1. I will explain what it is, U1. Okay. Let me play with the floor. The floor is two-dimensional. So you have the first direction and the second direction. So A1 is this direction, A2 is this one. And you have the function U. At every point, you associate a value. So this is the function U. At every point, you associate a certain number. Okay. And now what is this definition? you fix x1. So you fix a1, so it means in one coordinate, you fix it. And you look at all possible x2. You have your function. You look in this direction, x2, and you take the minimum value, the infimum value. So it's difficult to make a picture in 3 dimensions, but I will try. The floor is this. You have a1, a2, the 2 dimension. Now on this, we have a function which takes some value. So at every point, you associate a certain value on the top of it. And now you, for the first function, I fix a1. And I look at all possible values of a2. So I look at all possible values, and I look at the minimum value taken by this function. So look, I fix a1, and I took at the infimum, you can think about a minimum, at the minimum value of this function, which depends only on a2. And here the same, you fix now a2, so you fix in the other direction, and you look at the maximum value in the other direction. Okay? So it's really, you fix one direction, or you fix one value, and you look at all possible value in the other direction, and either you take the inf or the sup. Okay? And what is the meaning of this? Okay, let me keep this picture. This function represents something. Remember, this U1 is a payoff. So what you can receive for a given point, A1 and A2. So now if I fix A1 and I look at the infimum over all A2, A2 is a strategy by the second player, which you don't know. So you are taking the worst scenario. You are looking at the worst scenario, no matter what the other does, you take the minimum value, that your minimal payoff. So this is worst, it's a worst payoff for player 1. For player 1, when the first player plays A1. So if the first player plays the strategy A1, the other one is going to play something, and you take the minimum value that this guy is going to receive. It's the worst scenario for the first player. And what is this one? So it takes 1 more minute. This is the maximum loss for player 2 when playing A2. It's a maximum loss because you have to think about negative. You remember you have this relation between U1 and U2 with a negative sign. So the maximum value of this one is going to be the worst, so the biggest loss for the player U2. So think about it. But yeah, these two things have a meaning. Okay, and now we go on with one more definition. Do you have any question? You probably need to read this part 10 times before the next lecture. No, let me just finish the video. Now, for this V is equal to A1, A2, U1, when I write this, I mean a 2-player zero-sum game. I'm going to define lambda. This is now small lambda. This is still a lambda, but this is a small one. And you will be slightly surprised by the definition. I define underline small lambda as a sup over A1 in A1 of lambda, this one. And the other one is inf over A2 in A2 of this one. Okay. It's normal if you don't fully understand from the very beginning. Let's try to think about it. Player one can play with, the player can decide which A1 he wants to play. He knows that if he put a certain A1, the worst case, he will receive this value. But now you want to receive as much as possible. You want to increase your payoff. So you're going to choose the A1, which gives you the maximum value. That's why you take the supreme, the player one is going to take the maximum A1, I mean, the sup about this, the sup. And on the other hand, again, it's a little bit more difficult because you need to add a sign. The player two, this is the maximum loss, so he wants to minimize the maximum loss, so he will play A2, which gives you the infimum above among all A2. If you understand this, it's good. And these have a name. This lambda is called the lower value of G. And this one is called the upper value. And I will finish with this. I M plus, oh, maybe I should not erase immediately. What is the meaning of this lambda? This, okay. If we understand exactly the meaning of these lambda underline, so lambda underline is a minimum value, the minimum payoff that player one can guarantee for himself. So if he chooses the correct A1, he can guarantee this payoff. And on the other hand, this one is a maximum loss that player two may suffer this. But this is also equal because of the change of sign. This is also the maximal. This is also the maximal payoff for player. Because the gain of one player is the loss of the other one. Small observation, and I finish with this. You can wonder which one is bigger than the other one because it's a bit confusing. We first take a sup and an inf and so on. It's not so difficult to observe that they are not arbitrary. An observation. This guy of A1 is small or equal to U of A1, A2, U1, A1, A2. This is easy because this one was obtained by taking an infimum over all A2. This one was taking a supremum over all A1. So this is clear for any A1, A2, we have this. And now what about, we still have this. This one is a supremum over all this. So I'm claiming that this guy is always smaller or equal to this one. Can you see it? It's a bit surprising because suddenly you take the maximum value. But look, this guy is independent of A1. There is no A1 here. So it means this, which depends on A1, is smaller than this one for all A1. So even the maximal one among all these is smaller than this one. It's a bit tricky, but please think about it. When you take all these values, they are smaller than this one, which is independent of A1. So even the supremum is smaller than the right-hand side. So we have this relation. So it means if you look, the minimum payoff of player one is always smaller than the maximal payoff of player one, which is not surprising, but we prove it. And of course, if these two values are equal, we will get something, but we will do it next week. If not, it's more complicated. And then we are going to make a relation between this and Nash equilibrium. So again, I won't be able to tell you the best strategies for arbitrary games. I don't think it exists. Maybe the one in economics would know if it exists, or they would be rich and no more here. So the only thing we can do is to provide some framework, some definition, and some results for going in the direction of a best strategy. But for an arbitrary game, of course, nobody can do. Okay, that's all for today. Please don't forget that next week we have the lecture as usual. It's for this class, it's a Wednesday. We have already 2 reports available on the website, so you can have a look. And by the way, if you are working already on the same topic, it doesn't matter, you can still submit it. I accept that 2 reports are on the same topic because you shouldn't just copy and paste, of course, but you may be working on one topic and another student is working on the same topic. That's happened, this happened. Okay,